Welcome to Unit 6. In Unit 6, we get to really start using everything we've done so far this year. It's very exciting. We finally have some applications for our derivatives and for our limits, and then we get to actually see why these derivatives are important and how we get to use them. 4.1 is about related rates. Related rates is a pretty complicated concept, which means our problems are actually really easy. When we get to complicated concepts, we don't have really complicated problems. That's something that they do really nice for us in Calculus 1 by making difficult problems for easy concepts and easy problems for difficult concepts. It makes the whole thing a lot more attainable. So let's talk about what a related rate is. It's when one variable changes at a specific rate and how it affects the rate of something else changing. So we're going to look at how quantities with independent variables relate to each other, usually with respect to time. And then we differentiate each side of the equation with respect to an external variable, again, usually time. So we're looking at how things change over time. Those things could be unemployment rate, it could be the volume of a sphere, it could be the area of a circle. There are lots of different applications for this. So let's jump right in and start our first problem, and then I'll go over how we're going to do this. So a golfer hit a ball into a pond of still water, causing a circular ripple. If the radius of the circle increases at a constant rate of 0.5 meters per second squared, how fast is the area increasing when the radius of the ripple is 2 meters? So the first thing we have to do is figure out what all of our variables are. Since we have a circle and a radius, well, r will be our first one. And then t is the time. And a is the area. Now the question's asking us to look at how things are changing over time. How fast is the area of the circle increasing when the radius is 2? So we're looking at our rate of change. So we're looking at dr, dt, and how fast the area is changing is dA, dt. So in this problem, dr dt, they've given us here 0.5 meters per second squared. They're asking us for how fast the area is changing, and they're telling us that the radius is 2 meters. So we're going to start with the area formula for a circle is pi r squared. Let's differentiate both sides with respect to time. So I think I'll write it like this. So dA dt is going to be equal to, we're differentiating with respect to time, so it's 2 pi r dr dt. Remember that from implicit differentiation. We're differentiating the variable r with respect to time. So now my differentiated equation is dA dt equals 2 pi r times dr dt, meaning that the area of the circle with respect to time is changing at a rate of 2 pi times the radius times how fast the radius is changing. So let's plug in everything we know. We don't know our dA dt, so that's what our variable is. 2 pi, we know the radius is 2, and we know the dr dt is 0.5 or 1/2. So let's see, that's going to cancel, and I'm going to get 2 pi meters squared per second. So the area of my circle with respect to time is changing at about 6.283 meters squared per second when the radius is 2 meters. This is a really important point. It has to be when the radius is 2 meters. Otherwise, this part of the equation would change. So my area is changing with respect to time and the radius. Therefore, I need to have one of those held constant. And in this case, the constant holding is my 2 meters. We'll do many more of these, and hopefully this will make more sense. Now that you've seen one of these problems, let's go through the steps on how to solve these. The first step is you read the problem carefully, sometimes several times. Pay particular attention to the rate you're being asked to find and if possible, draw a picture to illustrate the problem. Step 2, identify the variables, assign symbols to them, and label the picture. Identify the rates of change as derivatives. Be sure to list the units for each variable and each rate of change. Indicate what is given and what is being asked for. So we're going to make a chart. After we draw our picture, we make a chart based on everything we know and everything we need to find. Then you write the equation that relates to the variables. It may be necessary to write more than one equation. In the area formula, we only had one equation, but you'll see as the problems get more complicated, we may have two equations, such as surface area and volume. So after we write the variables and the equations, we differentiate both sides of the equations. Then we substitute numerical values in and solve for the unknown rate. These steps work for every single problem we're going to do, so it's going to be useful for you to keep these handy. Let's take a look at example 2 on page 280. We're going to solve this problem step by step together. A spherical balloon is inflated at a rate of 10 meters cubed per minute. Find the rate at which the surface area of the balloon is increasing when the radius of the sphere is 3 meters. So step 1, we're going to read the problem carefully, perhaps several times. Pay attention to the rate you're being asked to find, and if possible, draw a picture and illustrate the problem. So we have our picture drawn over here for us, but let's reread the problem one more time. A spherical balloon is being inflated at a rate of 10 meters cubed per minute. So that's going to be important, so let's highlight that. We're being inflated. Find the rate at which the surface area of the balloon is increasing when the radius of the sphere is 3 meters. So now that we've read the problem a couple times, it's time to move on to step 2. Identify the variables, assign symbols to them, and label the picture. So here we have our picture labeled as our radius is 3 meters, but we don't have our rates of change identified. So let's talk about what we have. We definitely have a radius. That we have. I'm good with that one, my radius. But we're being asked to find the surface area, so I need a surface area for a sphere. And then a balloon is being inflated. We got to think about what inflated means. As the balloon is growing, think about what variable or what equation is changing. I'll give you a second to think. And hopefully you came up with volume. Volume is going to be our other formula for this problem. In addition, we're changing with respect to time. So time is our additional variable in this case. So the question's asking us when a balloon is being inflated at a rate, so that's my dv dt, at 10 meters cubed per minute. Find the rate at which the surface area, so that's my ds dt, is what I'm looking for. And I know my radius in this case is going to be 3. So let's think about our equations in the next slide. Now in step 3, we're going to write out our equations. So let's see, a surface area for a sphere is 4 pi r squared. The volume for a sphere is 4/3 pi r cubed. And we're looking for, step 4 asks us to differentiate both sides of each equation. I'm going to go up here for a little more room. We're going to differentiate with respect to time. So I have ds dt is 8 pi dr dt, and for the volume, 4/3 pi r cubed. Again, I'm going to differentiate with respect to time. So I have dv dt is 4 pi r squared dr dt. It's kind of interesting to note that the derivative of the volume is the surface area. So if we glance back, we have dv dt, which is 10 meters cubed per minute, and we're looking for ds dt. Notice the link between these two equations is this dr dt. I'm not given dr dt, but I can find dr dt and then plug it into the other equation. So while that wasn't explicitly stated as one of my variables that I need, I definitely need to be able to solve it to get to this problem. All right, so let's take a look at the volume. We'll keep going here, and we're going to substitute in what we know. So dv dt is 10, and we have 4 pi. My radius, they told me, is going to be 3. I'm just going to write that back up here. Squared, and dr dt is what I don't know. So my dr dt is 10 over 4 pi times 3 squared. And when I plug that into a calculator, I get dr dt is equal to 0.0884 meters per minute. So that's the rate that my radius is changing. But again, the problem asked us for ds dt, so we're going to go back and plug that in. And that's step 5, to use all the variables that I figured out and solve for the unknown rates. So I have my radius was 3. At the instant that the radius is 3, the radius is changing with respect to time, 0.0884 meters per minute. I'm going to plug that into my calculator, and I get 6.667 meters squared per minute. So my surface area is changing at a rate of 6.667 meters squared per minute when the radius is 3. Example 3 on page 281, a rectangular swimming pool is 10 meters long and 5 meters wide. It has a depth of 3 meters at one end and 1 meter at the other end. So here the deep end is going to be 3 meters and the shallow end is 1 meter. So I'm looking head on at the pool. This is 10 meters long, and if I was going to make the pool all the way, like to see all of it, this is where the 5 would come in. It would be like a right rectangular prism with a triangular prism underneath it. If the water is pumped into the pool at a rate of 300 liters per minute, at what rate is the water rising when it's 1.5 meters deep at the deep end? All right, so let's break this down by first writing down everything we know. Since I know the water is being pumped in at a rate of 300 liters per minute, I have my dv dt, because that's the rate my volume is changing, 300 liters per minute. Now it should be noted here that in liters per minute, I'm not accounting for my meters. So I need to convert liters per minute to meters cubed. So we'll take a minute and we'll do that. Before we get started with the rest of the problem. So to go from liters per minute to meters cubed, we have 300 over 1,000 meters cubed per minute, which is going to become 0.3 meters cubed per minute. Of course, I wouldn't expect you to have that memorized, but that's something that you'd want to look up and see how to figure that out. Okay, let's go back and keep reading about what we know. It says that at what rate is the water rising? So what's the water rising is my dHdt. That's my question mark, and it gives me when h is 1.5 meters. So we're looking at this triangle filling with water. And I want to know what the volume of my triangle here is. So the cross section of the triangle is going to be 1/2 the length times the height times 5. It's going to be times 5 because, as I said earlier, we had this, the pool is actually 5 meters wide. So we have, even though the drawing doesn't really show it, neither does my drawing very well, but we have this pool that goes all the way out for 5 meters. So now let's look at our similar triangles, because right now we have a length, a height, and a volume. And that's too many variables for this one equation. We need to deal with that length before we can do anything else. So let's take a look at our two similar triangles. The first one is here. It has a height of 2 and a length of 3. And our second triangle here has a height of h and a length of L. And by similar triangles, I know that these are proportionate. So 2 to 10 is the same as h to L. We're going to solve for L, so we'll cross multiply. We get 2L is 10h, meaning L is 5h. So now let's substitute that back in. So I have the volume is 1/2 5h times h times 5. So let's clean this up so it looks a lot nicer. We have 25 over 2 h squared. Now that we have our formulas all set for the volume that we're going to be using, let's take our derivative with respect to time. So I get dv dt is going to be 25h dh dt. Now once I've taken my derivative, I'm going to plug in everything I know. So we're going to look back and we know our height is 1.5 meters. This is why it was so important to get the dv dt into meters cubed here, because meters and liters don't really jive. I needed to get into cubic meters in order to make those work together. Okay, so we have 0.3 is going to be 25 times 1.5 dh dt. So my dh dt is 0.3 over 25 times 1.5. And I put this in my calculator, and I'm going to get dh dt is 0.008 meters per minute. So for every minute, the height of the pool is rising by 0.008 meters. Let's take a look at the next example. Example 4. On page 282, a person is standing at the end of the pier, is docking a boat by pulling the rope at a rate of 2 meters per second. The end of the rope is 3 meters above water level. How fast is the boat approaching the pier? When 5 meters of rope are pulled in, assume the rope never sags and that the rope is attached to the bottom of the boat at the water level. So they have a picture for you here in the book, but let's simplify it a bit. Hopefully you see that this is just a right triangle. We have this L, 3, and then X. So we're talking about a lot of different variables here. The L is the hypotenuse, the X is the base leg, and then my 3 is my other leg. So let's see if we can start labeling some of this. So we have two distinct things that are changing. The boat's moving this way, and the rope is moving this way. So we're going to have a dl dt and a dx dt. Now my 3 is staying constant, so the derivative of 3 is going to be 0, but we'll talk about that in a second. Since this is a right triangle, the way we're going to express these pieces is going to be using the Pythagorean theorem. So I have 3 squared plus x squared equals L squared. I hope everyone's clear about how I got those pieces. So a person standing at the end of the pier is docking a boat by pulling the rope at a rate of 2 meters per second. I want you to think, is that dl dt or dx dt? I'm going to give you 1 second to think about that. And hopefully you think that since this man is pulling, this is the thing that's changing with the rate of 2 meters per second. So my dl dt is 2 meters per second. I do not know my dx dt. That's the thing I'm being asked about. How fast is the boat approaching? Now this is going to become important in 1 minute, but we'll wait until we get there. So let's take the derivative of what we have here. So we have 9 plus x squared equals L squared. I'm going to do the dt for that, so the derivative with respect to time. The derivative of 9 is 0. The derivative of x squared is 2x dx dt. The derivative of L squared is 2L dl dt. Now, I don't have the x in this situation, but I do know that there are 5 meters of rope. At the instant that there are 5 meters of rope is when I'm looking for the dx dt. So let's solve that. If I know the height is 3 and my length of rope left is 5, x is what I'm looking for. So you can do Pythagorean theorem, or you might just know that this is a 3, 4, 5 triangle. So my x is 4. So the question is, when my x is 4, what is the rate the boat is changing? So now let's plug in what we know. We have 2 times 4 dx dt equals 2 times 5 times 2. So my dx dt is going to be 20 over 8, or 5 over 2, so 2.5 meters per second. This is telling us that at the instant that the boat is 4 meters from the dock, the rate at which the boat is moving close to the dock is 2.5 meters per second. Example 5 on page 283 talks about a lighthouse, and it definitely increases the level of difficulty. So let's take a read on this. A revolving light located 5 kilometers from the straight shoreline turns at a constant angular speed of 3 radians per minute. With what speed is the spotlight of the light moving along the shore when the beam makes a 60-degree angle with the shoreline? So we have our x is the distance between the beam and exactly how far away we are from shore. So point B is 5 kilometers from the shore, from where point A is in the ocean. And the beam is going around, and the question's asking us, when this is at 60 degrees, how fast are we moving? Let's define some of our variables. We have this x, which is the distance from B. We have theta, which is the angle in radians. And then our two things that are changing are dx dt and d theta dt. So this is giving us a hint about our equations. So I know that it's turning at a constant speed of 3 radians per minute, so that's my d theta dt. And I know I'm looking for dx dt. That's how fast it's moving on the shore. So using what we know about triangles, theta, we have opposite and adjacent, so we're going to use our tangent of theta is x over 5. That's the equation that we're going to be solving. Instead of having that 5 in the denominator, it might be more helpful to have x equals 5 tan theta before we do our differentiation. So let's differentiate with respect to t. So I have dx dt equals, the 5 comes to the right, the derivative of tangent is secant squared, theta, d theta, dt. So hopefully you've noticed that this is a special right triangle. We have our 90-degree angle here, our 60 here, and this one is 30 degrees. We're looking for theta in, I know that theta is 30 degrees, but I need it in radians. So let's multiply 30 by pi over 180, and my theta is pi over 6 radians. Now let's continue back to the problem and substitute back in what we know. We have dx dt equals 5 times the secant squared of pi over 6 times d theta dt, which is 3. All right, let's simplify some of this. So we have 15 secant squared pi over 6. So I don't know secant squared. It's not on my unit circle, but I can reduce that or rewrite it as 1 over cosine squared. And that is on my unit circle. So I have 15 over cosine of pi over 6 squared. Now pi over 6, hopefully you know what that is. But if you're not sure of what the cosine of pi over 6 is, you definitely want to look back at your unit circle for now. And you're going to see it's root 3 over 2. So I have 15 over root 3 over 2 squared. So 15 over 3/4 and that becomes 20. So on shore, the light beam dx dt is moving at 20 kilometers per minute. That's a pretty quick light. Before we finish this section, I just want to say that this is a really, really hard section. You have to use everything you have, every equation you've ever learned, every way of solving an equation you've ever learned, and then put calculus on top of it. So I want you to keep that in mind and not get too discouraged.